This is 1.3 day 1. We are going to simplify square roots by simplification, multiplication, and division. The first is just to review with you what a radical looks like. You don't need to write this slide down. The index in the examples we're going to do today all are going to have an index of 2. There's the radical sign, and then what's underneath the radical sign is what we call the radicand. This slide should look familiar to you. We talked about it earlier this year when we work with reducing radicals down to know the popular perfects. And we're going to focus this lesson on the perfect squares, this left-hand side. So for example, 6 squared equals 36. If you take the square root of 36, you'd be back at 6. So just making sure you remember these perfect squares. And then later on, we'll be talking about the perfect cubes, fourths, and fifths. All right, first example, go ahead and write this down. The square root of 16. You probably have the square root of 16 memorized. When we worked with these earlier this year, we said, identify the index. The index on all of these is 2. Then you'd rewrite 16 as 4 squared. Notice that the index and the power must match up for everything to cancel. So then your final answer is 4. This next example is a little more challenging because it's not a perfect anymore. So we want to look for a product of 2 numbers. So if I multiply 9 times 2 together, I get 18. And then I can break down 9 as a perfect, 3 squared. So what I can bring out of there is the square root of 9 is 3. Then I have a leftover of 2. Okay, next one, square root of 20. So you could probably skip writing this one down. Maybe be able to start to see what to break it down as 4 times 5. If you recognize that the square root of 4 is 2, then you just rewrite your answer as 2 squared of 5. Or you might have to rewrite it as a perfect first. 2 squared is 5. So there's a pair. So you pull out the 2, pop out the 2, and you're left with the 5 as your leftover. All right, going down to square root of 135. Working with some bigger numbers sometimes it becomes a little bit more complicated. So you're trying to look for what 2 numbers might multiply together that would be a perfect. So you might want to start with dividing. Does 135 divide into 2? No. Does it divide into 3? Yes. Does it divide into 5? Yes. So if I rewrite it as 5 times 27, that's 135. And then let's break down 27 as 9 and 3. And then the square root of 9 is 3. But then I have that 3 and 5 still left in there. So our answer is 3 square roots of 15. You multiply those 2 items back together in the radicand, and we're left with 15. All right, let's go on to now bringing some variables in. So the square root of 75x cubed can be broken down into 25 times 3, and then x squared and x. What's going to pop out is the square root of 25 and the square root of x squared. Those become 5 and x. And then what I have left is the 3 and the x as my radicand. All right, go ahead and write this one down. All right, I want to try to break down 245 in a product of 2 numbers. So just maybe use your calculator, take and divide by 2, divide by 3, or divide by 5. In this case, if I divide 245 by 5, I get 49 times 5. And then I can break down x squared, y squared, y squared, z z. Remember, the index in this problem is 2, so we're looking for pairs. If you want to break down 49 again, as 7 squared, 5, x squared, y squared, y squared, z. Anything that is a perfect square is going to pop out. So if I underline the perfects, square root of 49 is 7, square root of x squared is x, square root of y squared is y, square root of y squared is y. So those are going to go out in front. So I have 7, x, y, y. And then what's left over are the pieces that are not squared. So 5z. Now I'm just going to combine back together the two y's in the front as 7x y squared, and then the square root of 5z. All right, let's move on to multiplying square roots together. First example, the square root of 8 times the square root of 2. You can multiply two radicals into one radical if they have the same index number. In this case, they're both square roots. They both have an index of 2. So I can combine them into 1. So 8 times 2 is 16. And then we know that the square root of 16 can reduce to 4. Next example, square root of 5 times square root of 5. Again, you can multiply these two radicals together because they have the same index. They're both square roots. So that we would get 5 times 5, or 25. I'm just going to leave it as 5 squared. Remember, when we have an index and a power that match up, everything cancels, and we're left with 5. Very similar problem here. We have the square root of 3 times the square root of 3. Square root of 3 times square root of 3. If you look back at example B, that answer should be 5. Or in this case was 5. This should be 3. I'm just going to group them back together. 3 squared. Index and power match up. So our answer is 3. All right. Square root of 2 times square root of 18. Let's combine those together. So we get 2 times 18. Now, we could combine those two together to give you 36. And then the square root of 36, you probably recognize, is 6. If you don't, just break down 36 as 6 squared. And then you would get your 6. All right, let's go into adding some variables in. So question E says square root of 2x cubed y times the square root of 4x to the 4th. If we combine those two together, we have 2x cubed y times 4x to the 4th. So I'm just going to kind of clean up the terms here, put my coefficients together. I have the 2 and the 4, the x cubed, the x to the 4th, and then the y at the end. Now we're looking for pairs, things raised to the second power. So let's break down that 4, or you may recognize the square root of 4 is 2. Then I have 7 x's. I can break down to x squared, x squared, x squared, x to the 1, and then y. Again, I had a total of 7 x's there. So what's going to go out in front is a 2, an x, an x, an x, that 2x times x times x is x cubed. What's left over is my 2, my x, and my y. I'm going to stop the recording there and go to part 2.